Hey there, it's Shannon Mapchick Myers coming at you at about, a little after 1 in the morning on Monday, working late so that I can get this video out to my class for this week's module. So I hope everybody is doing well, and let's check out conditional statements. So if we go kind of extreme, we can look at a situation like this. If Shannon is beheaded, then Shannon dies. So if we were to let P denote Shannon is beheaded, and let Q denote Shannon dies. Well, if P is this part of the statement, we would end up having an if P, then Q, or equivalently, we introduce this symbol here, this arrow. So then you would have if P, then Q. Cool? This sentence is called conditional because the truth of the statement Q is conditioned on the truth of statement P. So this is kind of weird in logic. I mean, there's certain things that are logically true that aren't instinctively true. So logic is kind of another animal. So be open-minded. So that arrow symbol is a connective that can be used to join statements to create a new statement or a new statements. But remember, a sentence is a statement that is true or false, but not both. Well, how the heck can we find out if and when and if P then Q sentence is a statement? Your favorite, truth tables. Dun, 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 dun. All right, so let's check this out. So remember, P represents Shannon is beheaded. Q represents Shannon will die. So, well, our hypothesis of the conditional is true, and our conclusion is true. And this one is pretty clear to see. If I'm walking around without a head, I'm not going to live long. All right. Now, again, going with just setting up the basics, right? We did this last time. This is where it gets a little weird. Not the next one, but probably the last two. Now, if you have a true conditional statement, given statement, the conclusion cannot be false in an if P then Q statement. This is the only case where the if P then Q is false. So if the condition of beheading is met, there's no way that the conclusion can be false. Good so far? All right. Now, what if we have a false hypothesis of the conditional? Well, if the statement Shannon is beheaded is false, couldn't Shannon still die? I mean, what if Shannon got hit by a car, or Shannon, fell off the mist trail when she was hiking in Yosemite, right? So this still makes a logically true statement, right? So if the condition of beheading is not met, the conclusion could still be true. Which makes the connected statements true, right? And if the hypothesis is false, and if we also have the conclusion is false, it turns out that logically this is true. So if the condition of beheading is not met, well, the conclusion could also not be met. We don't know, right? So at the end of the day, in an if P then Q statement, unless there's a false conclusion given a true hypothesis, the new statement, so that if P then Q statement is logically true, right? So that's sort of a takeaway here. All right, so what happens if we were to switch P and Q in that last statement? So, I don't know, let's check it out. This here is all the same. And we have to look at it the other direction now, right? Because this is saying that, hey, Q is the conditional. So, and P is the conclusion. So, true, 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 right? That's all good. A false conditional could result in a true conclusion. But here's the deal. This is the problem child, right? A true condition can't result in a false conclusion. So this one is false. And the false is indeed true. So if you take a look at the truth tables, actually, let me go ahead and show you. Do you see that I did these in the same order, right? The P's and the Q's. And so the takeaway is they do not have the same truth values. So if P then Q went true, false, true, true, going down, and if Q then P went true, true, false, true. So the middle statements don't match. So they're not logically equivalent. All right, so this is important. P implies Q is not logically equivalent to Q implies P, right? Unless you have a stronger statement. So when we get to biconditional statements, then you could have a situation where your statement goes both ways. But that is later. All right, so FYI, just so you know, if Q then P happens to be the converse of if P then Q. All right, and we'll learn that officially in a moment or a few minutes. Okay, if P and Q are statement variables, the conditional of Q by P is if P, then Q, or P implies Q. It is false when P is true and Q is false. Otherwise, it is true. P is called the hypothesis of the conditional. And Q is called the conclusion. So let's check this out. Let's construct a truth table for the statement cosine pi equals 1/2 implies sine pi is less than 0. Well, I think a lot of you just completed pre-calc 2. So what do you think? Is it ever true that cosine pi equals 1/2? Heck no, it is never true, right? So this statement here, right, is always going to be false, the first part. So if this is our P and this is our Q, P is always false. So Q could be false or it could be true. So let's look at the truth table and check it on out. So P, Q, P implies Q. And hopefully you did the last section so you feel comfortable with these tables. So we decided that P is always false, but Q could be true or false, right? And we decided that because this is false, right? So here, what do you think? We always have this false hypothesis of the conditional, right? The only time you end up with a false statement, right, in this, conditional of Q by P is when the premise or the hypothesis is true and the conclusion is false. But in this case, the hypothesis is always false. So believe it or not, this here is a logically true statement. So this is logically true. All right, so a conditional statement that is true because its hypothesis is false is considered vacuously, hopefully I'm pronouncing that right, true or true by default. So now you can go and blow your friends' minds away by saying, hey, did you know that if cosine pi equals 1/2, then sine theta is less than 0? All right, so now let's take a look at order of operations for this connector. So in logical land, in the order of operations, the arrow then operation is performed last. So if you recall, the negation is first, and then the and the or statements are second. And remember that these were co-equal. And now we're learning that the arrow is last. Groovy? All right. So in example 2, let's construct a truth table for the statement form P or Q or not P and Q implies Q. So we've got our P, Q. So let's think about what we need. We are going to need P or Q, and we will need not P, and then not P and Q. So let's do this. We'll have our not P, we'll have our P or Q, and then we'll do not P and Q. And then, yes, it's busy here. Let's put some lines here. We also need to find out about that left side, P or Q, or not P and Q. And then after that, we can do that last bit. Which is P or Q or not P and Q implies Q. All right. So let's do some different colors at the end of the day. Let's do we'll do our conditional statement. We'll just get going. All right, so filling in the table, doing our usual stuff. True, 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 false, false, true, and false, false, just for P and Q. So if that is the case, going on to this next level, right, then if we take a look at not P, then we'll have false, false, true, true going down. Now, P or Q, remember that the only way that this is false is when both of them are false, right? So we're doing this comparison over here to look at over here. And so we'll have true, 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 and false. All right, so for not P and Q, let's see, we'll have now these two. Sorry if it's looking messy. Just want you to be able to follow along. So not P and Q. So these two here they both have to be true in order for the statement to be true. So we'll have false, false. The third one is true and true. So we'll have true and then false. We're getting there. So now, moving along, when we look at P or Q or not P and Q, we're now looking at these here. So this will take us over to this one. So it's an or statement. So the only time that this will be false is when they're both false, which is that last one. But otherwise, it's true. Groovy? Okay, so now we have to be careful. So we have this conditional, and the hypothesis statement is in this column, right? These are the truth values for that one. And then we're looking over at Q. So we're looking over here at Q, and Q is our conclusion statement. So reading kind of from right to left, we've got a true and a true and a true gives us beautiful, a true and a false. That's where it's going to be false, right? And we have a true and a true again. Is a true, and then a false and a false is a true logically. All right? So here are the truth values for that if-then statement. All right, so logical equivalence involving this then symbol. So the division into cases method, so this is kind of what we were doing, of analysis, is a great tool to show whether statements are logically equivalent. So we kind of started doing this with these truth tables. These were just the truth tables because we were just getting the truth values at the end of the day of this one here. But, and so that was the kind of the if this guy, then the Q. So now, we want to be able to go through and compare. So if we can see if statements are logically equivalent, right? So please construct a truth table to determine whether the statement forms if P then Q then R, and if P then Q then R are equivalent. So remember, when you've got 3 statement variables, you're going to have 2 cubed or 8 lines, right? 8 rows. So we'll have Q and R. And let's see what else. We need to have P implies Q. We also need to have Q implies R. And we need to have P implies if Q then R. And we need to have if P implies Q then R. All right, and so in this last box, we're going to be comparing these to see if they have the same truth values. here we go. So let's do it. So true, 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 false, true, false, true, true, false, false. And then we have false, true, true, false, true, false, 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 true, and false, false, false. Groovy? All right, so if P, then Q. So what we're going to be examining are, so if P, so true, 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 true. This is the one, remember, true, false is false. We have another true, false. And then the rest of them, since the hypothesis is false, they're all going to be true. Won't matter. Cool, cool? And these are all the ones we were looking at. All right, so now let's look at our next one. So Q then R. So Q then R. So true, true, true. True, false, false. False, true, true. False, false, false. No. False, false is a true. True, true, true. True, false is the false. And then the last two are going to be true. All right. So now what we want to look at is if P, then if Q, then R. So true, 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 false, false. That's when it's false, right? True, 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 false, true, true, and the rest you see, since you have a false hypothesis, the others will be true. Okay, so there's only one case in which we had a false statement. So let's check out the next one. Now we're going to be looking at P implies Q first, and then R. So true, 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 false. That's where we get a false. False, true, true, false, false is also true, true, true is true, but true, false is false, right? Then we go back to true, true being true, and then we have another true, false. So do you see that, we've got different truth values in a few places? Well, 2 places. So therefore, what would we conclude? We would conclude that if P, then if Q, then R is not logically equivalent to if P, then R, Q rather, then R. Cool, cool? All right. So, the negation of a conditional statement. Recall that the statement, if P then Q, is only false when its hypothesis is true and its conclusion is false. So, in this example, my husband is starring. Billy went fishing and Billy did not catch any fish, right? So here, why don't we let P denote Billy is fishing and then we can let Q denote Billy is catching fish. His first statement is saying and, isn't it? So we have P and good, not Q, right? Because he wasn't catching fish. Now here, when we're saying it is not the case that, negation. If Billy goes fishing, then Billy catches fish. So we have to group the if P, then Q. Cool so far? So let's see if they're logically equivalent, these two statements. So P, Q, we're going to need a not Q, a P implies Q, and then we'll have P and not Q. And over here we'll be comparing to see if not quantity P implies Q are equivalent. All right, here we go. So, true, 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 false, false, true, false, false. So, not Q will be what? False, true, false, true. P implies Q will be, so we're looking at these two, and we'll have true, 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 false, false, and then this last two must be true. Now, looking at P and not Q. So for P and not Q to be true, then both of those things have to be true. So the only case will be, so again, let's do it this way, P and not Q. So true, false, false, true, 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 false, 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 and false, true, false. So that was something learned from last lecture 2.1. Now let's take a look at the negation of if P then Q, that last part. So the negation is going to be the opposite of all of these, right? So we would get false, true, false, false. And hey, look at that. Looks like these guys are logically equivalent, right? So it turns out that P and not Q is logically equivalent to not if P then Q. Cool, cool? All right. So the contrapositive of a conditional statement. The contrapositive of a conditional statement of the form if P then Q is if not Q then not P. Symbolically, we have the contrapositive of if P then Q is not Q. If not Q, then not P. So notice how they switch around. So it turns out that a conditional statement is logically equivalent to its contrapositive. Next up, the converse and inverse of a conditional statement. So the converse is, suppose we have a conditional statement of the form if P then Q. The converse is if Q then P. We talked about that a little earlier, right? The converse, and symbolically, the converse of if P then Q is if Q then P. It's not always true. The inverse is if not P then not Q. Now that is not always true either. So the inverse of if P then Q is if not P then not Q. So let's take a look at this one below. If Shannon creates the video for section 2.2, then Shannon will be able to complete the Canvas video page for section 2.2. All right, so let's check it out. So the equivalent contrapositive form. So if Shannon is not able to complete the Canvas video page for section 2.2, then Shannon did not create the video for section 2.2. So that is the equivalent, note that word, contrapositive form. Now, the converse, we don't say equivalent in front of it because it isn't always. Same with the inverse. So, but the converse would be if Shannon is able for section 2.2 Then Shannon created the video for section 2.2. That's our converse. Now, the inverse would be if Shannon, so you help me out here. If Shannon does not create the video for section 2.2, then Shannon is not able to complete the Canvas video page for section 2.2. All right, so that's just a little example of, working with the actual words and being able to negate things and all that good stuff. All right, so only if and the by conditional. So if P and Q are statements, P only if Q means that if Q doesn't happen, right, then P can't happen. Or equivalently, if P, then Q. So what this is saying is that there's a logical equivalence between a statement and its contrapositive, right? So another definition, given statement variables P and Q, the biconditional of P and Q is P if and only if, that's a powerful statement, Q, and is denoted with a double arrow. It means that the statement goes both ways logically. So it means if P then Q and if Q then P. Right? It is true if both P and Q have the same truth values and is false if P and Q have opposite truth values. The text abbreviation for if and only if is IFF. So no, your math teacher is not misspelling if. They are representing if and only if. Okay, in the order of operations, this if and only if symbol is co-equal with the if, or the then arrow, the implication arrow, going one way. So the only way to figure out which is applied first is by use of parentheses. So let's check it out. Let's construct a truth table for the statement form P implies R if and only if Q implies R. So again, we'll need P, Q, R, and then just, I think P implies R, and Q implies R, so not a super long one. All right, so here we go. So we have our true, 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 false, true, false, true, and then true, false, false, and then false, true, true, false, true, false, 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 true, and false, false, false. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. So if P, then R. Well, what are we looking at here? We've got a true, true, so that will be true. True, false gives us a false. True, true, back to true. True, false is another false. And then all of these guys will be true. Now, if Q then R, see what that one is looking like. So true, 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 false, 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 true, true, false, false, true. True, 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 false, 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 true, true, and false, false, false. Now, well, geez, Shannon forgot a few things here, right? I forgot the other statement, the if and only if, right? So now, if we take a look at P implies R, if and only if, Q implies R. Let's see what we have. So remember, with the if and only if, they either both have to be true, right? Meaning the middle ones, or they both have to be false. So when comparing, we'll have true, true, so we get a true. False, false, so we get a true. True, true gives us a true. Now we've got a false and a true, so that's false. A true and a true is back to true. A true and a false is false. True and a true is true and true. And a false is false. So these are the final result of the truth. Well, it's a whole truth table, but those are the truth values for that last statement. All right, so almost done. Necessary and sufficient conditions. If R and S are statements, R is a sufficient condition for R is a sufficient condition for S means if R, then S. If Shannon is beheaded, then Shannon dies, right? R is a necessary condition, or R is a necessary condition for S means if not R, then not S. So sufficient would be if R, then S. Necessary means if not R, then not S. Okay? So here we go. Let's take a look at this statement from linear algebra. I have a few of my old linear students in the class. I thought I'd give you guys one. So we want to decide if this is the if and only if, or the if then form, or the only if form, one of those forms. So this says a basis set of vectors for R3 necessarily spans R3 and is linearly independent. Right? So in order to be a basis set of vectors for R3, both the spanning and the linearly independent part need to be true. So if I want to rewrite this statement, I can say a set of vectors is a basis for R3 if and only if, remember, the set spans R3 and the set is linearly independent. And if you haven't taken linear yet, maybe I'll see you later. All right, so this wraps up the lecture for today. I hope you have a wonderful morning, afternoon, or evening whenever you are watching this video. And if you like the video, please subscribe. Thank you. Bye.